Thank you, everybody, and thanks a lot for the invitation, the last minute invitation to give a talk here. As Steve said, I also don't get to work on Kuiper Belt objects as much as I would like to. I usually go to conferences on exoplanets, on protoplanetary disks. But as I say, planet formation is a, a murder mystery, and we needed to find clues everywhere that we can. And yeah, Kuiper Belt, the Kuiper Belt objects is a gold mine of information about how planets form. So let's see what, let me show them what I mean by this. So this talk will be based on, let me see how this thing works. Yeah, this talk will be based on these 4 papers that I have been working on the past few years. So let's dive in. The first one starts with this plot. This plot has already been shown here a couple of times. The density versus mass, it's usually plotted in terms of radius, but I'd like to plot that in terms of mass for 2 reasons. You know, mass is more fundamental than radius, and also the fact that, and I'm going to go back to it, as you see, there is a big gap there in mass, right? From 10 to the minus 2 to 10 to the minus 2. Is this a laser or a lightsaber? It looks like a lightsaber when you hold it. There you go. There is a big gap here, right, between 10 to the minus 3 and 10 to the minus 2 times the mass of Pluto. It's about 10 to the 19 to 10 to the 20 kilograms. I'm going to go back to this. But what I would like to highlight here is well, something that has already been said, is that there is a change in density as you go here from the low mass objects to the high mass ones, right? And it's kind of harder to explain why that is the case. Why is it that we don't have high density low mass objects or low density high mass objects? The current explanation or the previous best bet is that, well, as we heard from Steve, is that there is a gradual removal of porosity through gravitational compaction as these objects grow in mass. So then you can start here from low density objects at constant composition. That's the key thing here. And these curves here are giving you different rock mass fractions, starting from half, so half rock, half ice, 70% or 80%. And then the green curve here captures most of these objects, right, for this slow compactification. Well, there is a problem here with this explanation. Steve already mentioned what one of these problems is timing, right? Because too much aluminum-26 is going to melt these objects if they form early. You need to wait 4 million years. And I think it is underappreciated the fact that 4 million years is a lot of time. And maybe we don't have that much time because it's not just waiting 4 million years for these objects to form. You still need to have them grow through pebble accretion while the disk is there. And the disk doesn't live that much. So maybe this 4 million years here is a bit too much. So how can we form them earlier while still avoiding aluminum-26? So the assumptions here are constant composition at birth and growth, and that the growth happened via planetesimal accretion. Well, so these are the things that I would challenge here. So these objects, right, we think that they form, at least the low mass ones, via the streaming instability. I mean, it doesn't need to be that, but that's our current best bet, a mechanism that has been shown to work in models. So if we take that, so what is happening here is that you have dust, right? You have the pebbles in the disk, they drift inwards, and this drift itself is unstable. That means that it's not constant density drift. It is a mechanism that builds these voids and these overdensities, and then the overdense regions get dense enough to reach critical density for gravitational collapse, right? The mechanism is shown here. You have a drift that is moving inwards. Oops, sorry. Have a drift here that is moving inwards. It will be deflected azimuthally, will capture more grains, and then it will reinforce the overdensity as it goes. So how about the assumption of constant composition? Once you, once you form the pebbles, they are in an environment that they will keep scooping up the micron-sized grains, be them silicate or icy, and keep growing. But there is a mechanism here by which ice can be removed, is what is being shown here in this plot. So this plot shows here the radius of the grains and the height above the mid-plane of the disk. These lines here, the red line and the orange, are the heights at which ice can be removed, simply because you heat a layer that is hot enough for ice to evaporate from the grain, or because you are above the optical depth one for UV from the sun. So that will also remove ice. So this mechanism is photodesorption. If the grains can reach these layers, they will have their ice removed. Not completely, but some, right? So they will reach these layers here if the grains are small enough. The big grains, they don't get lofted in the atmosphere too high because they have too much mass, right? The turbulence cannot bring them that high up. So you end up with a population of grains that never gets above these heights. They can keep the ice, and a population of smaller grains that do, and then end up getting their ice removed. So to simplify this, right, I'm interested in the first order approximation here. You would have them big icy grains and smaller dust grains, bimodal distribution. In reality, that won't be the case. You're going to have both of them being dirty ice with different proportions. But let's do first this approximation and see where we get. So you can run again a streaming instability calculation now with these two types of grains, the icy grains and the silicate grains, and then see what we get. So that's what is shown here. So this is the full disk, and then split here into the icy grains and the silicate ones. What you see is that because the icy grains are bigger, the streaming instability kicks in the ices only. That's where you see the filaments, right, and the planetesimals. Almost nothing is happening in the smaller dust grains. There are some little dots that you can see here if you squint. But most of the action is happening in the ice. So the first planetesimals, they end up being ice. I'm plotting here the ice fraction. You see that they're mostly icy here. They're mostly formed with the big icy grains. Okay, so once we form the planetesimals, what happens next? What happens next is that they scoop up the pebbles in the disk, and they keep growing them by this process, by pebble accretion. So you start here from the micron-sized dust grains, coagulate them to the pebbles. The pebbles both form planetesimals via the streaming instability and are accreted by them to then make the cores of the rocky planets or the icy objects. And the growth can continue if these objects carve a partial gas gap in the disk. They will stop the flow of pebbles. They can cool down, they become gas giants, and if they don't, they become ice giants. Right, so what is pebble accretion? Pebble accretion is what happens if you have gas around, because gas makes the motion dissipative. So the pebble, as it's orbiting through the gas, it is suffering a headwind, it is suffering drag, it loses energy, makes accretion much, much easier, right, than if you had the planetesimals that do not feel gas drag. If you don't have gas drag, the problem is a scattering problem, right? It's conservative. That's not the case for pebbles that suffer gas drag. So that is shown here. So there's a mass now. You switch on the mass and it clears up like it's a vacuum cleaner. Just grabs all of the pebbles in the the calculation. The accretion rates orders of magnitude higher than for planetesimal accretion, especially at the distances of the Kuiper belt, or where the giant planets are now. Now, there's a catch here. There are different accretion modes that depends on the different radii, the different scales in this problem here. So you have the capture radius, which is usually the cross-section for capturing planetesimals. As you see, that's quite small. And then you have the Bondi radius. That's not the Bondi radius for accretion of gas, as we normally think of it. But the Bondi accretion rate for the Bondi radius for accretion of the pebbles against the different speed that gas and pebbles orbit in the disk. And then the other length here is the Hill radius of the object. The regime where they are will depend on the ordering of these radii here. If the Bondi radius is smaller than the Hill radius, you accrete only from the Bondi. If the Bondi radius is bigger than the Hill, you cannot accrete beyond the Hill, so you are in the regime of Hill accretion. And there is another scale here, which is the scale height of the pebbles in the disk, which will tell you if the accretion happens in 3D or in 2D. Right? If you have a much bigger accretion radius than the pebble scale height, your cross-section is essentially just a line, so that's 2D accretion. Whereas if you're embedded, you offer the full cross-section, and the accretion is 3D. Normally, the Bondi radius is in 3D and the Hill radius is in 2D. I'm saying usually because I recently checked that for AGN disks, and it turned out that the Bondi happens Hill happens in 3D there, but that's for another audience. So you have here the mass accretion rates. The violet line is the actual accretion rate, and as you see here, the transition from the focus accretion, so only the capture radius, to the Bondi, and then you cross here the transition mass, which is very close to also where the accretion passes from 2D to 3D. And then beyond that, that's Hill accretion. Now look at the masses here. You're looking at the mass of the Moon, Ceres, right? So the Kuiper belt objects, if they form around here, right? So Pluto is about what? 10 to the -4 Earth mass. You're deep into the Bondi regime, right? So contrary to what you usually see pebble accretion being used for, which is to make the cores of the giant planets. So for the Kuiper belt objects, we're deep into the Bondi regime. So it's the 3D accretion that matters. We'll see soon why that becomes a problem. So this is a calculation where you start from the objects that are formed by streaming instability. I put them in a pebble accretion integrator, and that's what happens. You just wait and wait and wait, and they are not growing. If you see them, they're here, right? They're not, you can see that there's some change happening here, but not much. You can wait a Hubble time and nothing is gonna happen here. So what is missing? What is missing is the fact that there is a subtle effect here that doesn't matter for the Hill accretion, but for the Bondi accretion regime, it does matter, is that there is a Goldilocks effect. There is a size for the pebble that accretes the best. When it comes to Hill accretion, you are accreting pebbles from all over the Hill sphere. The color coding here, yellow is for the small pebbles, the red is for the medium-sized pebbles, the blue one for large pebbles. Right, Papa pebble, Mama pebble, baby pebble. That's what you have here. As you see, the big ones, the blue ones, even the big ones get accreted in the Hill case. But if you follow the blue ones, they're just scattered, they're just like planetesimals. The point is that the large pebbles are too big. They cross the Bondi radius too fast. The pebble needs to have a response to drag within the time that it takes to cross the Bondi sphere. If the pebbles are too big, they will behave just like planetesimals and not gonna get accreted. So the assumption that where most of the mass lies, which is the biggest pebbles, will give you the bulk of the mass accretion rate, you would be right for the Hill accretion, but dead wrong for the Bondi regime case. For that case, you need a polydisperse size distribution, meaning pebbles of all sizes, so that you can capture the optimum, the medium-sized grains here that accrete the best. So that was a tour de force to calculate that. I'm not going to bore you with the math, but that's why I wrote one of the papers I showed first, was to solve that problem. It necessitated a big update on the theory of pebble accretion, which is what I'm showing here. So these plots may look a bit confusing. Let me show what is happening here. So this is the size of the dust grain, the size of the pebble. The mass of the seed that is doing the accretion, and color-coded here is the mass accretion rates, the differential mass accretion rate per pebble bin. And the three regimes are shown here: the hill accretion, the bond accretion, and the geometrical one. So the mass accretion rates here are lower than in the hill, but you never get there to the hill regime if you start from a mass, so 10 to the minus 4 again, right? That's the size of Pluto. You start with much, much less than that. There is no way that you will hit hill here. You are deep here into the bond. And this plot is the same thing, except that is normalized by the mass accretion rate of the biggest pebble in the calculation. So whenever you are in this red region, you have higher accretion rate for smaller grains than the biggest grain. That's how to read this plot, right? Everywhere, if you apply hill accretion or assume that the biggest pebble gives you the biggest mass accretion rate, you would be fine, except in this red region here, which is precisely where we expect then the planetesimals, the Kuiper belt objects to be. And these are the mass accretion rates that we get if we integrate now that figure and the integrated mass accretion rate over all of the pebble size distribution. What you see here, the gray is the monodisperse, right? If you only consider one size. So for the hill accretion, it's fine. You are underestimating now if you use polydisperse, because you don't have only the biggest pebble. You have also pebbles that are not accreting too well. But in the Bondi case, you see here that there is a big change. It doesn't look big, but that's just because the mass accretion rate range here is more than 10 orders of magnitude. But you're looking at 2 orders of magnitude increase in the pebble accretion rate, and an onset of Bondi accretion, 2 orders of magnitude down in mass too. So instead of starting around the mass of Pluto, you can start 2 orders of magnitude less massive than that, and accreting at 2 orders of magnitude higher. So back to that calculation. There should be a video. Okay, of course, it's in my hand. Yes. So there you go. Now they are starting to grow. And there you go. You can climb that. Oh, and you overshoot. You reach Aries, but so this is Aries here. You reach Aries, but you don't reach Triton, Pluto. And I think this is Haumea. Right, that's because of the assumption. As I said, I assumed that the pebbles were, that they formed the icy pebbles, right? And then accreted the silicate pebbles. That's the model tree here that I'm showing. I'm showing here on the upper plots, the internal density of the pebbles, so pure silicate, about 3 grams per cubic centimeter. Ice would be 1, right? So I tried other also different models. So the model 3 is the one that you see here. If they start icy and accrete silicates, then yeah, you can form Aries, not the other ones. The next thing that I tried was the model 1 here, which is a power law. Why do you ask me? I'm an astronomer. We like power laws, so yeah, why not try that? Right? So you start here from silicate to ice, right? And that's the ice volume fraction of the pebbles. That doesn't do a good job because you accrete too much ice, right? So then I added a dial. So they're pure silicates up to a point, and then power law, that's the model 2. And then with that, you can reproduce Pluto, Triton, and Haumea. So that's the model 2 here with this constant up to a point and then a parallel after. And see then, yeah, you can capture them. So what's going on in terms of distance then on this model? That calculation was for a distance of 20 AU, so we changed that to see what is the range that this model works. At 10 AU, you can reproduce the masses, you can actually form very massive objects, but they start creating ice too soon, so the densities don't reproduce. You reproduce this up to about 22 AU. Beyond the 25 AU, what is happening here is that the mass accretion rates are too low, right? So you don't get the high masses we see. So according to this model, you would be able to form the objects that became the high mass Kuiper belt objects between about 15 to 22 AU. And that's a range that fits quite well with the Denis model, right? Where the giant planets were initially. Before the migration, the outward migration of Neptune. So what was going on the lower distances at 10 AU? So these lines here are the mass accretion rate, the rhombus here for 10 AU, the stars for 20 AU, and here for 30 AU. There is a window of silicate accretion. Color-coded here is the ice fraction of the pebble that gives you the best mass accretion rate. So think of it as a typical ice fraction of the pebble that is getting accreted by the seed. At 10 AU, you see that you form a mass of about 10 to the minus 2 Pluto mass, and immediately you start creating a lot of ice, right? So that doesn't work too well. At 20 AU, yeah, you hit here the sweet spot for the silicate accretion. At 30 AU, yeah, you are in the silicate window, but the mass accretion rates now are 10 to the minus 10, so that's too low. So that does not work, even though the pebbles that you would need would be there. Right, so let me switch gears and, well, not switch completely, still talk about this plot, but in a different way. That gap, right, that I mentioned prior, I actually came to a meeting here last summer, specifically to ask the experts if that gap was real. And most of the answers I heard was like, oh, I never noticed that gap there. And I thought, all right, okay, so we are on to something here. As you see here, right, you have the low mass objects, you have the high mass objects. I color-coded and symbol-coded here the different objects in this plot. So the cold classicals are the black ones, the red ones are the resonant objects, blue are the scatter disk. You clearly see that the cold classicals are only on the low mass side, right, of the gap. So there is a difference in population here. It makes sense that the low mass objects would be here on this side of the gap because they are equal brightness, right? Even though they are sorry, let me go back here. Even though they are low mass, they have companions that are of about the same brightness, so they're easy to find. As Proudfoot showed, right, there's this plot here. It was shown before. There is a difference, not only mass, but also in system architecture as you pass from the small mass objects to the high mass objects. On the high mass objects, you usually have small moons in tight orbits. And then here, you have, on the low mass, have equal mass objects in wide binaries. I agree also with Proudfoot that if these objects were not binaries, I wouldn't care about them. So I would love if you found moons for Ixion and Varuna so that we can see where they lie here in this plot. So these here, they're easy to find because of that. These ones, right, they're easy to find if the moon is also big and if it's far out. But if you have a small moon that is close by, of course, yeah, you don't need me to tell you that makes it much harder. But the interesting bit that this says about how planets form is the fact that the high mass end of the low mass side of the gap, so going back here, right, this end here coincides with the truncation of the cold classicals. Right, so if I trust the OSIS survey, they say that the population of cold classicals is complete to 400 kilometers. That fits exactly what we find then from streaming instability calculations, right? There is an exponential fall here. So the cumulative number n equal 1 is right there, right, where this mass gap lies. This is plotted here in magnitude. I don't deal with magnitudes. I'm a theoretician, but well, you can check there what these objects, where this gap falls then in terms of magnitude, and there you are. So the binaries are missing here. You see a dearth between 4 and 5th magnitude. And the red beans here are the distribution of all KBOs. So that mass gap is not depopulated. The objects exist there, just that you know they're hard to I mean, it's difficult to find the binary. So the low mass side, yeah, that's the code classicals, and this side here, that you would have the low mass objects in this gap here. Maybe they are there, right? I mean, you can see maybe they are lurking here, but it's hard to identify them as binaries. But there is more to it than just that. It's not just that they're hard to find. Why is it that they're hard to find? Falls back into the question of what is happening here, right? Why there is a population difference between the low mass and the high mass object. So go again back to how they form and how they grow. So these objects here, they formed by streaming in instability, but they did not undergo pebble accretion because they're too low mass. These objects here did, right? So this plot has also something lurking in it. So this is the semi-major axis of the binary normalized by the Hill radius of the binary. And then, yeah, you see the mass gap here. There's these two objects there in the gap. So this is the line here that is normally quoted for the boundary to the ultra-wide binaries. I usually don't use acronyms in talks, so, but yeah, UWBs. So only the code classicals, apart from this object here, which objects there is? Borosici, maybe? Morsominus, all right. Wait, I did not include Morsominus because Morsominus did not have a density determinant. Oh, but it has mass. Okay, thanks. Yes, yes. By the way, observers and people who like occultations, please care about this object. Please, 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 like, because this arrow bar here is awful. That's the only reason why I'm plotting here to 5, which is hiding actually where the interesting things happen. In this object too, which is a Borosici, right? This is 2002 WC19, right? Yeah. Yeah. I remember some of the phone numbers. It's not only exoplanet people that like to call objects by phone numbers. Yeah. So what is happening here then? These objects, right? They don't form on. They might form with at these distances, at these separations. But if they do, they are easily ionized in the interaction with Neptune. And actually, there is a recent paper by Campbell that shows that even the ultra-wide binaries here, they are not primordial. Because if you start with primordial ultra-wide binaries, even the interaction with other planetesimals will easily widen them and ionize them too. So these ultra-wide binaries here started as lower separation and then became ultra-wide binaries. So the same thing should have happened here too. We should see also some objects here in the high mass end that were all that should also have ultra-wide binaries, and we don't. Why is that? So we don't know, but maybe the answer to that lies in the growth process, in the pebble accretion process. So they start as low mass objects like this one, and they scoop up the pebbles, right, growing, and something in the pebble accretion process probably disrupted the binary, the original one. So these objects here lost the primordial moons during the growth process. Now, it could be that dynamical accretion shrank the binary, right, until they got to contact. That's one of the possibilities. I'm going to be working on that next. So I don't have yet results of that to show, but ask me again in a couple years time, and then I might have an answer for that. Also, the fact that as you get deeper into the gap, turn out that again, right, as Proudfoot showed, these objects become like quite hard, right, to do an orbital fit. You have non-Keplerian effects. So I'm plotting here the radius of the object over the semi-major axis of the binary, which is a proxy for how strong the non-Keplerian effect will be, because this is the coefficient of it. I mean, the distance factor of the J2. The strongest non-Keplerian term. So as you get deeper into the gap, then this starts to become more and more important. And you already see here, right, in the orbital fit for Huya, there is precession. So even the job of finding out what the mass is for these objects become more complicated. Finally, I'd like to mention one thing that got me wondering is what happens to the moons. Since I started thinking about this problem, I realized that actually there is mass and density determination. There's one article, right, by Brown and Butler, 2023, that did a mass and radius determination for Vanth and Dysnomia, the moons of Orcus and Aries. As you can see here, they would fall right into the mass gap, right? Now, if we believe that these objects, that the mass of these objects is not, well, I mean, if we think that they formed by impacts, right, then their masses would probably not be primordial. Well, prior to the Kiss and capture model, the models we had would say that these objects probably lost about 3 times the mass during the collision event, even though they formed from an object that even though it lost mass, it actually samples the density of the impactor. So this is the same plot here, but with proto-Vanth and proto-Dysnomia with 3 times the mass, but the same density. What I found weird here then in this plot is that Orcus does not follow the density trend, but Dysnomia does, right? If you multiply their masses by 3, Orcus now kind of follows the trend and Dysnomia does not. So what is it saying? That maybe in the impact, Orcus, Vanth, sorry, it did lose a lot of mass. So it now has a mass, but well, it has too high density for the mass being where it is. But Dysnomia did not lose that much mass. It is in the density where you would expect an object of that mass to be. And Huya here in this object, they seem to also not follow the density trend. So maybe they are fragments of a denser object, right? And now are occupying this mass plane. With that, I still have 10 minutes. Okay, thank you. So I'd like, oh, that includes questions. Okay, right. So I'll go fast through this. This is a work that I did back in 2021. Of course, I was working on my protoplanetary disk things. I was actually writing an article with Orkan, right, back at that time. That was January 2019, and then came Arrokoth flyby. And there we were trying to understand how planetesimals form, and you guys give us one, you know. So, yeah, we had to stop everything we were doing to figure out how that object formed. So so I will quickly go through the results here. The idea is that so these objects, right? The arc of the two lobes formed, of course, individually with a distance between them, and they are orbiting then in the disk, and there is a headwind from the gas. This headwind is of about 50 meters per second, so which is much more than the orbital speed, right? That these two lobes orbit each other because it is such a low mass object. So there we go. I calculated here what is the orbital solution if you have drag then with this wind. So that's what you see here. You have a very slow loss of energy. So the semi-major axis is almost constant. Eccentricity quickly goes to 1, and then angular momentum follows. The eccentricity is quickly drained too. So that's what the solution looks like. It's a very interesting orbital solution. You increase the eccentricity at constant semi-major axis, right? So yeah, you lose angular momentum at constant energy. Well, it turns out that it doesn't work, at least not for the distances of the Kuiper belt. So this is the plot here of the effective orbital, the drag time, in terms of millions of years. And what you expect here in terms of distance. Right? And as you see here, they all converge at about like 30 AU. So this is the typical pressure gradient here in the disk, the red line, so 0, 1, 10, 50, and 100. What's going on is that the drag force itself passes from being linear to quadratic as you decrease density. So that works quite well as long as you are in the drag regime that is quadratic. Because in this case, the wind speed does not average out. But if you are in the linear case, it does. The angular momentum that you lose on one side, you gain on the other side of the orbit. And arc of the lobes are in the transition here. These contours here are for Reynolds number. So you are at Reynolds number 10, so closer to linear than to quadratic. So we needed something else. Drag alone will not to do the job. So I thought maybe, the inclination, right, was 99. So Kozai-Lidov oscillations maybe would do the trick. But of course, there is much more complicated than pure Kozai, because you have that these objects are triaxial. So you have a permanent quadrupole. They can also raise tides on each other. So this is a model where I implemented tidal forcing, permanent quadrupole, and drag on a Kozai calculation. This is the classical Kozai. So read here the initial inclination and then the distance. So you would have contact if you are within this region here under. If you include all of these processes, you end up with some regions here that don't have contact anymore. This is known here because this is J2, right? It leads to precession. So you kick it out of the resonance that leads to Kozai up to this point, and then you can start having contact. What is interesting is that drag opens up a window of contact where in the classical Kozai you didn't have. So you now can have contact up to much bigger distances and higher inclinations than you had before. This is what's going on here in semi-major axis inclination and pericentric distance. The calculation with no dissipation at all, that's just classical Kozai. You don't even see that's the green line is hidden behind the other ones. The actual solution is the red one. So you see there is a decrease in semi-major axis, but now you have chaotic incursions of inclination. And within about 2 million years, if you have the chaotic oscillations in inclination, and on top of that, you also have drag that is decreasing the energy, you can lead to contact. That's the line here, contact at about 2 million years. So I'll just put my conclusions here, and I will be happy to take questions now. Thank you very much.
All right, brilliant. Thank you ever so much. And we do have some time for questions if anyone's in the room wants to ask anything. I had one, and I'm really glad you put this graph back up again, because it seems like you have two models, and one of them was able to fit. And I'm not sure what the final plot was on the top right hand side of it. So the start, that one, yeah,
Yeah, Eris.
that was Eris. Okay, you have one model that's able to fit that very nicely, and the other one that bends over and fits Pluto and Charon very nicely.
Yeah.
You never found one that sort of does the wiggle down and then wiggle up again, right?
Oh, this one here?
No, to the right. That one. Because that one, those data sort of fall off, right? And it looks like,
well, this
Todd's going
this
mad
is
right
Qualler,
now.
actually.
Interaction. So does it? See, that one falls off. Sorry. Yes, I can. Sorry. All right. So this one falls up and it kind of hits these three, right? But there's nothing that goes like, and then magically sort of zooms up here and can catch. So you have to you can either fit those three, right? Or you can fit that one. Can you comment on why that might be the case?
Yeah, there is a very good question. Thanks. So why is it that we need different models, right? So one model fits here and one model fits Aries. To me, that shows that there is something weird about Aries, right? That maybe it lost the mantle, maybe there were collisions there, but then we just heard that the Aries has an albedo of what, 0.93. So I don't know. We would need to understand much more about Aries to pinpoint that question. Thank you.
So on your modeling to merge the Arakoth components, that's cool, but there's one other constraint, which is that they have to merge at very low speeds.
Right.
So I'm wondering if you're able to do that.
Right. Yes. They merge at the escape speed, which for that mass is about 6 meters per second, which is too high, but that's the escape speed if they were perfect spheres. The elongation makes it possible to drop that speed to about 3. So that's closer to what is needed.
So you in the Kanas paper, this is occurring. I mean, you see, you were talking about the sweet spot. That means that there was a special Stokes number that you were running your simulations on. What era of the disk evolution is this? Is this like 3, 4, 5 million years? I mean,
Right.
because that definitely the disk is now dissipating, bringing the Stokes number into the Goldilocks zone. So can you comment on what era this is likely occurring in?
Right. Yeah. We started at time 0 here is from the DSC AIs. Yes. So
it's
when you
T
see
equals
they are
0.
5 million years is after CAI. So that's T0. Yeah. I didn't add to this calculation anything about, you have to start 4 million years afterwards. That's exactly what I was trying to avoid. The evolution of the gas disk is an e-folding time of 2.5 million years.
So that this development is taking place and the Stokes number is
Yes.
evolving through that
Correct.
simulation. Okay, I didn't appreciate that before. Okay,
Well,
thank you.
you're an author in the paper.
I know. It's sad.
I'm going to jump in, Bill, really quick, because I had Orkan's question. I just want to amplify it a little bit. Thank you, Orkan, for asking that. The only question I have is a little bit more is to understand, you're making the very smallest bodies on this plot in the first million years.
Correct.
You're making Pluto within 5.7 million years?
Yes.
Cool. Okay.
Correct.
I'm done.
All right, we have 40 seconds, so ask fast.
I'm a bit confused. Are we making icy bodies first or silicate bodies first? Because you seem to have two models.
Icy bodies first.
Okay.
Yeah.
You
What
have
prevents
20
the
seconds.
overshoot? Why don't we go to Mars size? I mean, it's like,
Oh, it can. It for sure can. Yes, they can overshoot. So yeah, you have to stop the accretion of pebbles to coincide with the timing of the dissipation of the disk, right? So what we show here, if I go back to, and I know that the time is almost done, I have to go back a lot here, is that there is a range of distances where you overshoot, right? If you form them at 10 AU, you overshoot them. If you coincide the disk to end at about 10 million years, that's the end, right? That happens at 22 AU. Right, but if you form at 10 AU or here, you will overshoot. Yes.
10 million years is sort of long now.
It's long, exactly. Yeah, I would be happier with the disk that is about like 3 folding times. 4 is kind of less so. Yeah. So a gas disk that lives for. I mean, we need. Is Steve here in the room? Yeah, we need. I think that we have constraints, right, for how long the solar nebula lived from the timing that Jupiter opened the gap. And don't quote me on that, but maybe 3 or 5 million years or so. Yeah.
All right. I think we'll probably have to leave it there